Hi, I'm Matt Giamou, and I'll be talking resource efficiently to you about optimal communication planning for distributed loop closure detection. Multi-robot systems rely on cooperative SLAM to safely and effectively carry out tasks like search and rescue or autonomous urban mapping. Inter-robot communication is needed to maintain accurate localization and mapping across all robots in the fleet. For robot systems with limited battery, wireless bandwidth, or computation, carrying out CSLAM can be a challenge. To solve this problem, we investigate resource-efficient distributed place recognition through optimal data exchange. Distributed place recognition is essential for inter-robot loop closure detection in CSLAM. In this work, we consider the optimal communication policy between two robots with measurements that have been identified as candidate loop closures. Candidate loop closures are edges that form a measurement exchange graph between measurements taken at different poses belonging to each robot's trajectory. We seek the optimal cost communication policy that ensures that all candidates are examined. Cost is defined in terms of data transmitted, computation required for each robot, or the weighted sum of both. Typically, robots would send all candidate loop closures to other members of the fleet. This approach leads to redundant information sharing, as only one agent needs access to both measurements of a candidate loop closure. A simple improvement involves one robot sending all its candidate measurements to the other, like Robot 2 in the exchange graph figure on the right. While often helpful, we prove that this monologue approach is only optimal if a generalized version of Hall's condition holds. In all other cases, the optimal exchange policy is a non-trivial dialogue involving two-way communication. We demonstrate that the optimal policy can be obtained by determining the minimum weighted vertex cover of the exchange graph. While it is NP hard to obtain an optimal solution for more than two agents, the two-agent case can be efficiently solved by relaxing the problem into a linear program. Robots 1 and 2 engage in an optimal dialogue for the given example graph. In order to test our method, we use sequences 0 and 6 from the KITTI odometry benchmark dataset. Each dataset was divided into two halves representing two distinct robots' trajectories. Candidate edges were formed with one of three methods: distance between poses, overlapping camera field of view, and visual similarity score. For each method of candidate generation, we varied the corresponding thresholds on visual similarity, distance, or overlapping field of view. For all cases tested, the optimal policy was able to significantly improve on the naive monologue policies.